Greetings, this is Mr. Mortensen, and you are watching a video about everything there is to know about functions. Alright? Now, we have just entered the Labor Day weekend, and I hope everyone is having a great time there. There was a tiny amount of homework given to every student, and it requires you to show all your knowledge on graphs and determining whether or not they are functions, as well as a lot of the vocabulary that we've been using. So I thought I would take this time to go over and review a little bit of what we've learned. If you're struggling with the homework, I hope you find this video helpful. And this may also come in handy if you're reviewing for a test. Alright, let's go over some of our stuff here. So we have this first function, and we're told, alright, we have f of x equals just some letter. They said a, which remember, a lot of our functions we are asking, is it increasing, is it decreasing? I know we haven't focused as much on what happens when it's just a nice flat line or if it's constant. But it seemed like this would be a good area to kind of start us off with. Alright, so if it's constant, that means it's neither increasing nor decreasing. And as we can see here, in this particular case, we have ourselves a continuous line. If we wanted to see something more along the lines of a discrete function, we would have these isolated points, or I've had a lot of students say, they're the dot functions. Let me go ahead and darken that up a little bit. I realize you can't see it. Alright. Okay, so that's a little bit more what an isolated set of points there, or a discrete function, would look like. And that's going to be one of the terms that you're going to want to know. Discrete versus continuous. Also, I notice that sometimes when we say find the maximum and minimum, that always comes up a little intriguing. Remember, our maximum is going to be our greatest output, or one way we can think of that is it's going to be our largest y value. Or you might say the greatest, the biggest number that goes up as far as a y value, where our graph basically is going to be the highest for y values. So let's think about that, finding a maximum, and look at it with respect to this graph. When we look at it, we see that it only has one y value. In this case, it looks like it's going through 4, or this point A that they've determined. So really, all these points here, that makes up our maximum. Alright, well, what about our minimum? Alright, our minimum, that's going to be our smallest y value, or our lowest output. So our minimum, that's going to be our smallest y value. Right? And as we're looking at it in this case, again, there's only one y value that we have. So for this first case, it's just going to be a, since that's what we know it is, or it looks like it's about 4, if we're going along the graph there. We can actually zoom it in so you can see what I'm saying here. So you'll notice here it looks like it's going right through about 4. Alright? Or we can just say that we know that it's going to be the point A, which they've determined for us. Alright. Let's tell you what. Let's try this on one that's going to be a little bit more interesting then. Alright, so let's try and find the maximum and minimum for this absolute value function. We have f of x equals the absolute value of x, and the graph is being shown here. And so go ahead and try and see. Can you find the maximum and the minimum for this graph? Go ahead and pause the video at this time. See what you can come up with. Alright. Let's go ahead and let's find it. So in this case, we'll look, and right off we can see, okay, what's our lowest y value going to be? If we look, it's growing outward and going in an upward direction. Each of these are going to be going upwards. But here, this is going to be our lowest point that we can come up with. It's 0.00. So that means our minimum that's going to equal 0. Right? Now for the maximum, we don't really have one that's showing up on the graph. Right? It's just going to keep on going on and on forever. Well, that's going to mean what some people would say is the maximum in this case is going to be equal to infinity. Right? Some would say, oh, well, there's not one that we can see on the graph, or if we're getting technical, the maximum in this case is going to be infinity. All right? So, let's look at this one here, the greatest integer set. This one's a bit of an interesting graph because we haven't seen anything like this in our classes. So, first off, let's evaluate. First off, does this one even look like a function? Alright, and it's saying, alright, we have these lines, and what they've determined here is that each value is going to be listed as the closest integer just beneath any value. So, for example, 1/2, that's going to go, see, f of 1/2, that's going to be equal to 0, right? Or f of 3/2, that's going to equal 1. Alright, so that's how they give us this mapping. And so let's actually kind of determine, is this a function? And how are we going to do that? We're going to just look at a couple of vertical line tests. Alright, so if I draw up, it's a terrible line there. Alright, so if I draw it through one of our arbitrary lines, it looks like, okay, I'm only going to touch at one point. Seems like it's a winner then. Let's check the ends here. Let's see, let's check it on this one. So if I draw my vertical line, I'm doing it right. Let's see, so I go through the point 1 there, and you'll notice I go through the open bubble, and then I go through this closed one. Well, what it's telling us here is that that open bubble, that doesn't actually count as a point on the graph. The closed one does. So that's getting a little more technical than what we're going to be touching with most of the time in class. But if we ever have that open bubble case, that still means that we have ourselves a function. So this one is a function. So I want you to think about this. Do you think this graph is continuous, discrete, or could it be something else entirely? In this case, we'll notice that all of our points aren't really connected. We have all these jumps. So some might say discrete. But remember, discrete, we had to have these isolated points all by themselves. So this is a good example of a function that is neither continuous or discrete. Alright, so let's try looking at a couple others here. Alright, let's try one of our function families. Okay, so we're going to look at this type of function here. What type is it? We're going to call it, we're going to call that a quadratic. There we go. Alright. The reason we're going to call it a quadratic is it's got this lovely symmetry, where it has vertical symmetry, but also it has an interesting growing pattern. Remember from your notes, we were able to identify this one as being a special case by saying, alright, if we have just x squared, that means at the point 0 we're going to have 0. At positive 1 and negative 1, we just have positive 1 and positive 1. And we also had 2 and negative 2. Those just go to 4 and negative 4. So it starts to get this exponential type growth, but it keeps that symmetry going on both sides of its vertex. Alright? That's going to come in real handy when we start trying to identify our graphs or our functions when all we're given is just a table of values. We'll be coming up on that. So just keep in mind that's what our quadratics are going to look like. And then let's play with one other type of function here. Okay, let's try our one that we have listed just below here. Oh, you didn't see that. All right, we have our exponential function. An exponential is just described as any number being raised to our input value, or anything that's in the form of a to the x, or I believe in our books we even said a times b to the x. I believe that was the definition we gave it from our book. All right? Anything in that format. So we got to play around with these a little bit in class. We got to see if b is greater than 1, and if the sign of this whole thing is positive, then we have a graph that's going to look just like this one, where our function approaches 0 from the left and shoots off at an incredible rate as we go to the right. But we also saw, suppose we just have a fraction that is less than 1. Might go that way. Might go in that way. Right? Where it just still stays above the axis, but now does that. Or we also had another case. I'm going to grab a red pen for this one. So this is b less than